In section 13.5, we'll look at the fundamental theorem of calculus. And it seems ironic that here we are, like 3 days from the end of the course, and we get to the fundamental theorem of calculus. It's the name of it. Okay. Here's what it says. If f is an antiderivative oh, sorry, hang on. Wrong line. My bad. If f is a continuous function on a to b, and big F is an antiderivative of little f, then the definite integral from a to b of little f of x dx is equal to big F of x evaluated at b, the upper limit of integration, minus big F of x, or big F, evaluated at little a, the lower limit of integration. So that gives us the formula for computing definite integrals exactly. So what we did yesterday was come up with the Riemann sums. We took partitions of size 2 and then 4 and then 8, and we could have kept going and things like that. But the calculations get tedious if you don't have a computer. As it turns out, there is a simple way of evaluating all of those definite integrals and finding the exact area. And it is the fundamental theorem. And you basically find an antiderivative of the function you're finding the area under. Evaluate that at the upper limit, evaluate that at the lower limit, and subtract. And that's the area. That's the connection between integration and derivatives and antiderivatives and the like. All right, let me show you how this works. What is the integral from 0 to 2 of x squared dx? So the first thing you need to come up with is an antiderivative of x squared. So we'll just use those rules that we learned the other day. Raise the power by 1, divide by the new power. So the antiderivative of x squared is x cubed over 3. And now we bring back our good friend, the evaluation bar. Remember this? The big vertical bar? The last time we used this, chapter 11. We put a number at the bottom. We put a point at the bottom, and we evaluated x and y. When we use the evaluation bar with integrals, we put the lower limit and the upper limit much like it was the integral itself. And this tells us that we need to do top minus bottom. So we'll evaluate the 2 inside this function minus the 0 evaluated in that function. And 2 cubed is 8, divided by 3 is 8/3. The right side is 0, and so the answer is 8/3. So, what does that mean? If we had the parabola, y equals x squared, from 0 to 2, and I wanted to calculate this area exactly, that area is equal to 8/3. recapping, we found an antiderivative. We used the evaluation bar to denote that we needed to evaluate it at 2 and at 0 and subtract those results, top minus bottom, and then we finished the calculation. All right, with your partner, go ahead and work example 2. And when you get that, see if you can draw the geometric picture, just like the picture I have drawn here.
So now it's like 3? Oh, yeah.
Well, it's not a graph. It's a straight line. No. Go back to the original. Yeah. I'll show you.
Yeah, so then we'll go to 7
Yeah, so you would do the percent one, but you evaluated minus. The interval is 2x and x squared. This is, see, what the graph is, that's right. Right. And it goes from 0 to 0. You need to do 2x minus 7. That's correct. You forgot to say. You agreed to say. Yeah, so, what's the end goal set? Do them all the same time. Do them all the same. All right, let's check it. So first, you need to find the antiderivative. The antiderivative of 2x is x squared. Then the antiderivative of negative 7 is negative 7x. Evaluated from 3 to 7. Divide by 2. Yeah, 2x squared divided by 2. Yeah. All right, so this would be 7 squared minus 7 times 7 minus 3 squared minus 7 times 3. You need to use parentheses so that the negative distributes appropriately. 7 squared minus 7 times 7 is 0. Minus 3 squared is 9. Minus 7 times 3 is 21. And so that's 0 minus negative 12, which is positive 12. Now, let's look at the picture. When you go to graph these, you graph the original integrand, not the antiderivative. Because what an integral represents is signed area from the integrand, just like we did yesterday. So we're going to take y equals 2x minus 7. So that's a line that starts at negative 7. And then if I go over here to where x is 7, 2 times 7 is 14, minus 7 is 7. So this actually goes up to the point 7 comma 7. Now this whole thing isn't part of the integral. The integral only goes from 3 to 7. So it is at least this piece here. If x is equal to 3, what's the y value? Should be negative 1. So that means when x is equal to 3, the y is negative 1. So I'm going to put it right here. So the integral is the area from the right piece minus the area from this left piece. Because remember, if the portion of the graph is below the x-axis, that results in negative contribution. It's a negative area. The portion that is above the x-axis results in positive contribution. And together, those work out to give you 12. The top minus the bottom area. All right. Now, what if we've done this problem slightly different? Remember, the fundamental theorem says you can use any antiderivative to do the calculation. What would have happened if the antiderivative I had chosen was x squared minus 7x plus 4? That is an antiderivative of 2x minus 7, certainly, because the derivative of that is 2x minus 7. What happens when you do the evaluation? You get 7 squared minus 7 times 7 plus 4 minus 3 squared minus 7 times 3 plus 4. It cancels out. The 4 minus the 4 cancels out. So you might as well use c is equal to 0 because it's going to cancel out anyway. And you're left with the same answer. All right. All right, let's look at example 3. We have the integral from 0 to 1 of x to the 2012 power dx. We need to find the antiderivative. What's the antiderivative of x to the 2012? divided by 2013. Raise the power by 1, divide by the new power. Evaluate from 0 to 1. So this would be 1 raised to the 2013 divided by 2013 minus 0 to the 2013 over 2013. What is 1 to the 2013 power? 1. So that's 1 over 2013. What is 0 to the 2013? 0 divided by 2013. Still 0. So the answer is 1 over 2013. Questions? Okay, let's look at number 4. Number 4 is the integral from 1 to 4 of 3 times x squared plus x squared times 2x plus 1. Ignoring the definite part of the integral, the 1 to 4 part, we still need to find the antiderivative of this integrand. Suggestions? Use substitution. Yeah. Does everyone see a function and its derivative sitting in there? That tells you that you need to use substitution. So what do you want u to be? It's two different u's. See? What? Somebody?
X squared plus x.
That's right. X squared plus x. So what is du? 2x plus 1 times dx. Solve for dx. That would be du over 2x plus 1. Now, with a definite integral, we need to add 2 more steps. We need to find out what numbers should replace the 1 and the 4. The 1 and the 4 are x numbers. We're going to replace those with u's, so we just need to find out what u is when x is equal to each of these numbers. So think of u as a little function of x. So u of 4 is going to be 4 squared plus 4 by plugging in 4 into the relation between u and x, this top equation. That would be 20. And what is u of 1? Yeah, that's 1 squared plus 1, which is 2. So now we have the definite integral, not from 1 to 4, but from 2 to 20. Because we have replaced the limits of integration with u limits and not x limits. We have 3. We have u squared. We have 2x plus 1 times du over 2x plus 1. Two x plus 1 cancels. That's the limit. That's the integral from 2 to 20 of 3u squared du. Good so far? All right. Now integrate. What's the integral of 3u squared? What is it? Yeah. U cubed. Now, here's where the process is different from the other process. Because we substituted in the limits for u, we don't have to go back. these numbers, the 2 and the 20, those are u's. So we simply evaluate those numbers, and that's the answer. So this is 20 cubed minus 2 cubed, which is 7,992. So the process differs from the old process in that we don't have to go back. In an indefinite integral, you are looking for an answer with x, so you have to go back. Here, you are simply looking for the number that represents the definite integral or the signed area. So if you make the substitution early, like we did here with the numbers, then you don't have to go back. They're the same things. If you had not made the substitution early, then you would have gone back, and this u would then again been x squared plus x, and you would have used the 4, which would have been 4 squared plus 4. Well, sorry, it would have been, it would have been that cubed, right? So 4 squared plus 4 would be 20, which you would then cube, which is what we did anyway. And minus 1 squared plus 1 is 2. You would cube that, which is what we did anyway. So you're just saving yourself some time. Tyler?
I understand that the du just goes away, but why does it go away?
The du is part of the notation that represents the width from what we were doing yesterday. So, and the 3u squared represents the height. So the integral sign and the d whatever go together. Yeah. If you sort of think of it, you can think of it in other terms. You can think of 3u squared du as the differential. So when you integrate it, you don't have the differential anymore. You're going backwards. Yeah. Other questions? All right, go ahead and work example 5 with your partner. Be sure to substitute out the limits. Be sure to change the limit. Now, your view is just x plus 2. So your limit should just be 13. And then, if you remember your algebra, no, still in the bottom. Still in the bottom. What's the integral of 1 over 1? What's the interval? No. What's the interval? Well, in other words, what did you take the root of? Let's see what 1 over 1. You got to remember some algebra. The integral of u is the net line. That's the more integral. And if you're going to use u, you also need to change your limits. So run your limits through the questions. You got to substitute because what you have is not just 1 over x, it's 1 over something plus x. Maybe a contribution from the chain. You don't, we said you're missing your u, you're missing all substitution. So, you're missing it. Yeah, right here. This is just, there's no x here. Equal x plus 2. That's the right idea, wrong operation. So what is it? Is that 5? Okay. How do you get 5? Come back. How do you combine two logs that are subtracted? Okay. Yeah. Let's try to get the exact answer by combining those two. That's probably the right answer numerically. I don't know. You don't subtract. What do? You don't subtract. It's another rule. It's a different rule. What is it? What is the rule? What is the rule? What is the rule? Divide it. That's very good. Okay. Now what is the Okay, yeah, so great. If you change the limits, then you don't go back to the x. U is actually so you should, in fact, when you put the plus just put the evaluation from 13 and 5 right there, and then work that out. All right, we're going to check it in 2 seconds. I want the exact. Substituting this out. Whatever you're substituting out as an expression, you just put the variable in for that spot. This is is 1 over x plus 2. X plus 2 is 2. So 1 over what represents x plus 2. And so then what represents dx is. What's the interval of 1 over u? All right, let's check it. All right. So we're going to let u be x plus 2. So du is dx, and dx is du. U of 11 is 11 plus 2, which is 13. And u of 3 is 3 plus 2, which is 5. Using those as the new limits and the new function, we get the integral from 5 to 13 of 1 over u du. The integral of 1 over u is the natural log of the absolute value of u, evaluated from 5 to 13. So this would be the natural log of 13. No absolute value bar is needed because 13 is positive. Minus natural log of 5. No absolute bars needed. And then how do you subtract two logs? You divide. So it's natural log of 13 over 5. Questions? All right. What's the question? What's the question?
Why is it 13 over 5?
Uh-huh. When you subtract two logs, you divide. You remember this? You don't remember this? What about this one? Log in base b of x plus log in base b of y. That is log in base b of x times y. So the sum of two logarithms is equal to the logarithm of the product of the arguments. The difference of two logarithms is the logarithm of the quotient of the two arguments. Interesting story. So, which is harder to do, adding or multiplying? It's a softball question. Which is harder, adding or multiplying? Multiplying is harder. I'm not talking about like you can't do 5 times 3. I'm talking about like big numbers. Big numbers. Multiplying is harder. So what they would do if they had really big numbers to multiply is they would change them to logarithms, the two numbers. They would take the log in some base, usually base 10. And then they would add those results together to come up with a new number. And then because they took the log, then they would undo the log. That's the, you know what they call that? You're not going to like this. You're going to hate me. What's the opposite of log? Anti-log. Anti-log. No one uses that anymore. No one does that. But that's what they took the anti-log, which was, if you took it in base 10, then that was 10 to the power. And then that would come up with a number. Because it was in the log book. They had these log tables. You know what I'm talking about? Let's go to the computer. Can you see this? Top secret password. This is how I learned to do logarithms. That's how old I am. Log tables. Not that kind of table. That is the wrong table. There we go. There it is. That's what is that? Okay. All right. So here's the question. So what is the log of 5? There it is. So the log, let's see how this works. All right. So log, so you want to do log of 13 over 5. Okay. All right. 13 over 5 is 2.6. What's 2.6? That's 0.414973. Now, what's the log of 13? That's not on here, is it? Oh, and by the way, these are probably logs in base 10, which, as far as doing logs, yeah, it'll be the log in base 10. So we're sort of strayed away from what we were wanting to do, but this will work out fine. So we don't know that one because it's too big. But we do know this one. We know log of 5. (0.698970). So the log in base 10 of 13 is 0.414973 plus 0.698. Is it 7? It's 97. 970. And so add that up. So this is the thing. You would add this up to figure out everything else here. So what do we get? Oops. 0.4149733 plus 0.69897. So this is 1.113943. Okay? Now, the log in base 10 of any number 10 or bigger is 1 or larger. So we know that this number is going to be bigger than 10, right? So this is 1 plus this. Now, we look for that number on the chart, the bold part. So where is 0.113973? All right, where's that? Does anybody see it? We're looking for 0.113943. What is it? 1.3. Did you say 1.30? Huh? Did you? Uh-huh. Okay. So this is log in base 10 of 10. That's 1, right? That's the same thing. Plus log. Well, hang on. Let's do it this way. Yeah, I'll do it this way. Log in base 10 of 1.3. All right? 1139434. Yeah, plus. All right. Now, what do you do when you add two logs together? Multiply. What's 10 times 1.3? 13. Boom! Right there it is. Did you see it? Did you see it? That's the way the logs work. That is the way the logs work. So that's log in base 10 of 13. So that's what you would do. So how do you figure this? How do you figure this? What is log base 10 of
this exact question.
24? All right, calculate log base 10 of 24. Log base 10 on your calculator is just regular log. Let's see if you get faster. 1.38. Yeah, that's right. Okay.
So it's Mr. Ray.
So how do you do it? So this is really log base 10 of 10 times 2.4. 24 is 10 times 2.4. And then you split it up. So it's log base 10 of 10 plus log base 10 of 2.4. Log base 10 of 10 is 1. Log base 10 of 2.4 is 0.380. So therefore it's 1.380. That's what they had to do. Multiplication was very hard. So instead of multiplying, they reduced everything down to adding and then used logs and then they did anti-logs and stuff like that. What was the question? What was the question? Why do you
What's the difference between log and natural log?
Common log is base 10. Natural log is base E. Because we can do logs in anyways, as long as it's positive and not negative. All right. So, did that answer your question?
Yes.
Okay. That's the safe answer. No, but what they would have is they would have textbooks, and they would have these log tables in the back, and then you had to get good at the log rules in order to use the log tables because they only put up. See, where does the log go from here? It goes from 1 to about 9.99, right? Yeah, because then at 10, then you're using rules like that. You extract a 10, and then you use adding and stuff. Yeah. Okay. You're welcome. All right, now let's look at this application problem. Example 6. A company manufactures X high-definition televisions per month. The monthly marginal profit in dollars is given by P prime of X is equal to 165 minus 0.1X, for X between 0 and 4,000. The company is currently manufacturing 1,500 HD TVs per month, but is planning to increase production. Find the change in monthly profit if monthly production is increased to 1,600 HD TVs. Right. Suggestions? It's a fantastic suggestion. So, what are we looking for? What are we looking for? Change in profit, right? So, what is the new profit level going to be? No, how many are we going to make? 1,600. So the profit at 1,600 minus the profit at the current level of production, 1,500. Now, does this look familiar? A function evaluated at a number minus that same function evaluated at another number. So what is that actually? That is actually the integral from 1,500 to 1,600, but it's not of the p function. You integrate the derivative. So it's the integral of p prime of x dx. And luckily for you, you were given p prime of x. So does everyone see how this relates to the antiderivative in the integral? You're looking for a change. That change comes about from taking the integral of the marginal function and evaluating at the endpoints. So what you're really looking for is the integral from 1,500 to 1,600 of 165 minus 0.1x dx. All right, go ahead and do that one with your partner. Find the integer. Oh, you don't need u on this one. This one works out straight up. You can integrate 165 and you can integrate x, so you don't need any substitution to do that. The integral 165 is 165x. The integral this one has oh, you read it wrong. 0.01x. What's 0.1 divided by 2? Evaluate bar evaluates what's behind it. What is the 1,000 chicken? 1,000 feet. 1,000. Dollars. Oh, see. Oh. Okay. Once you integrate, you no longer visit EX. Evaluation.
Just the value and
Use parentheses. All right, let's check it. So the integral of 165 is 165x minus the integral of 0.1x. So that's 0.1x divided by 2, 0.1x squared divided by 2. Evaluation from 1500 to 1600. Now you can reduce that number there if you'd like before you do this. 0.1 divided by 2 is 0.05x squared. 1500 to 1600. And then you plug in both of those. So here we go. 165 times 1600 minus 0.05 times 1600 squared minus 165 times 1500 minus 0.05 times 1500 squared. And if you work that out, you get $1,000. So that's the increase in profit. Questions?
And that 1,000 is within that dividing that 0 to 4,000? Is that what?
It's not the 1,000, it's the 1,600 and the 1,500.
Oh, okay.
Because those are the X's.
So that 4,000 is kind of irrelevant? Since those
No.
numbers are between
No, it's relevant. It's the 1,600 and the 1,500 have to be between 0 and 4,000. Yeah. All right. Last topic for today is average value of a continuous function. So, average value, the formula for average value is 1 over b minus a times the integral from a to b of f of x dx. All right, example 7. Find the average value of f of x is equal to x squared minus 2x plus 8 over 1 to 4. All right, I'll set it up for you, and then I'll let you work on it. You tell me how to set it up. So how do we find average value? What's the numbers? 4 minus 1 times the integral from 1 to 4 of x squared minus 2x plus 8 dx. All right, so go ahead and work that out. Then we'll check it, and then I will show you what the average value does for us.
So
Why we have to use an integral.
we just work it out as normal, but what do we do with that average value of 1/3?
Yeah, you multiply by it. Yeah, you're gonna do the integral.
Oh, that's going to
Times
be
a
multiplied.
third.
Okay.
Tell me how much cost for it?
Yeah, it's constant on the outside already. Yeah. This 1 over b minus a is multiplied by the integral. It's 1 over b minus a times the integral. So you work out the integral and multiply it together.
Can you work out the integral?
Yeah, you got to compute this. You got to compute this first. Compute the integral first. You can do that again. Or you can do it ongoing. But it's just 1/3 time. It's like a constant. Yeah, you could even split these up like this if you want to. Yeah. All right, so you should have got 10.
I said you had multiplied by 1/3.
I did, right there.
Where?
Right there.
Oh, you did.
See, I just did the integral right here.
Oh, I think you did.
You can do it all at once, or you can just do the integral and then come back and do average value. Average value would be 1/3 times that. All right, so were you able to get 10? 10. Right. Now, what does the average value tell us? Well, it's this value right. Let's see. Where are we taking this from? We're taking this from 1 to 4. Right there. The picture doesn't look right. Let me check the picture. Seven, 4, 16. Okay. Here it is. All right. So the average value is the following. Let me erase this and start again. So what does the integral represent itself? The integral itself represents all this area, right? All right. The average value, we'll put this in green. So the average value would start off is 10 right here. The average value is the height of the function, that if I drew the rectangle at that height over the same base interval, they would have the same, let me do it in outline. They would have the same area. So the green rectangle and the shaded blue area are exactly the same. And so basically what's happening is this piece of area up here falls into that piece right there. And it fills it out. So the average value is the height of the function that would make the same area over the same base.